So this is one of the last talks, and in this talk I'd like to talk about graphs with this little fancy title here. So let me begin by saying what I mean by a graph. I do not mean this type of graph, but rather I mean this type of graph consisting of vertices and edges. So the circles here are the vertices labeled with capital letters. And the edges are, in this case, depicted by arrows going from one vertex to another, which in this case have a direction, but that's not necessary. Some of the edges I have labeled. And so that is the kind of abstract mathematical structure I'm talking about when I say graph. Graphs do occur naturally. So for example, typical social networks are graphs. Followers on Twitter. So the people would be the vertices, and the edges, there would be an edge if somebody is following somebody else. But you can have dependency chains if you have certain things which depend on each other, packages in a Linux distribution or whatever. You can have computer networks where the network connectivity is depicted, the topology is depicted by the edges. You can have articles and citations, and I'll show an example of this later. You can have hierarchies. So wherever you look in nature, graphs occur. And indeed, you obviously know about relational databases. Any relation is actually a graph. You only have to take the things you relate to each other as the vertices, and whenever two things are related, you draw an edge. So graphs are essentially the same as relations. Sometimes they are directed, sometimes they are undirected, and so that's what I'm talking about. So this is a Hadoop conference. So people are probably familiar with Hadoop and Spark tools to work with graphs. The details of this don't matter, but suffice to say that the modern way in Spark to work with graphs is that you have a data frame somewhere with your vertices and a data frame with your edges with a particular shape. Namely, in your edges, you have to have two columns, one called source and one called destination. And that is essentially your edge going from the source to the destination. And then you form a graph frame, and that's somehow the modern way, as opposed to GraphX, which is still usable, which has some other means to work with graphs. Anyway, what you can do with things, then you can ask for the in degrees, that's the number of edges pointing into a vertex, or the out degrees. You can do queries on that. You can do statistics on the vertices, looking for whatever. And you can, for example, do things like that. And you don't have to know the details. You can already see what's going on. This syntax here asks for an edge going from a vertex, which we denote by A, to a vertex, which we denote by B. And we denote the edge by E. And then we have a second edge going from B to C. And then we have some kind of filter condition, and we count. So that is a typical question to a graph. It says, here's a graph. Give me all the paths of length 2 in the graph under the condition that the ID of the vertex is this here, that is, that they start in a certain vertex, for example. But there's other things. The famous Google PageRank algorithm is something which can easily be done in Spark, and lots more. So I'm not saying this is bad, rather to the contrary. This is all very nice. And all these methods work particularly well if you have global questions for your graph. If you want to do something like PageRank, which looks everywhere in your graph. Because then Spark can really play to its strengths, namely quickly going through everything, and so things like that. Now, quite often in graphs which occur naturally in the data you already have, you have other types of questions. Quite often, you want smallish ad hoc queries. the one I've shown here with a path starting in a particular point, that is somehow a very small local question. Ad hoc means that you have lots of different of them, but they are all small and should be answered rather quickly. In particular, for each of these queries, you want to bring the latency somehow down. For larger ones from minutes to seconds, and for smaller ones maybe from seconds to milliseconds. But you want to run a lot of them. I'll have examples of this in a second. That is something you can very well do with GraphX or Spark or graph frames, no problem. But every single time you do something, you have to somehow fire up a large engine, and behind the scenes a lot of things have to happen just to answer your rather simple question. So let's look at a few examples. In a social network, you might want to see the friends of the friends, that is 2 steps, but starting just at a single person. That doesn't look at the whole graph, rather it starts in some particular point and maybe just finds 100 things. Or if you have a kind of dependency chain, you want to start somewhere and then find everything from which it depends, or the other way around. Or if you have some kind of articles and citations, some bibliography database, you just want citations of one article, or maybe citations and then what they cite, or going backwards and forwards in the citation graph. Anyway, just for one article. Or you want to find the descendants in some hierarchy of somebody, whatever, but only for some person. And then I could imagine a lot of situations where you have to do a lot of these, but they are just coming in from some kind of web front end for somebody or something like this. Anyway, what turns out is that GraphX and Spark, although it's very good for graphs and it's well done for graphs and it's designed to do that, this kind of workload cannot really well be handled. And so what I want to suggest in this talk and present to some extent is that there is an alternative tool in the box. Namely, you could use a graph database. So let me explain what a graph database is. Well, obviously you know what a database is, but a graph database is one that stores graphs. Well, that's not a big surprise, and that is nothing really fancy because essentially every database can store graphs. The crucial point is that a graph database can do graph queries. So what are graph queries? Typical questions for a graph, and we have seen already some, is you want to find certain paths in the graph according to some pattern. So one pattern could be starting here and then 2 steps, or 2 to 7 steps, or a path starting here and then in the 3rd step the label on the edge is something, or something like that. Or you want to go out and start somewhere and explore the graph and find everything in the vicinity, maybe up to a certain depth or not. Or you have 2 vertices and want to find the shortest path. These are typical graph queries, and the method to do that is something called graph traversals, and I will explain this on the next slide, what it is. But crucial to all of them is that the number of steps we have to go to answer the question is not a priori known. That is typical. Okay, there are certain queries. For example, if I ask paths of length 2, then the length is known. But sometimes the length isn't known. For example, in the second case, or when I just ask for a path of an unknown length. And the crucial part why I mentioned this here is the following. If you store your graph in any odd database, say a relational database just in 2 tables, that is fine when it comes to storing and retrieving. But it is not fine if you have queries of that type. Typically, in a relational database, you would have to have a very complicated SQL query where you have different cases as to how long the path is. And the path of length 7 would typically be a join, a multi-join with say, what do you say, step 7 and an edge table and a vertex table, that would be a join of length 14 or something like that. Very bad. Doesn't work very well. But in a graph database, these guys do work well. And here's why. This is a graph traversal just done on stage. So here's a graph. And what I do in this graph traversal is I start somewhere and write down the label of the vertex. Now I explore all outgoing edges one after another. That is, the first one I would find would maybe be B. So I put B on my list because this is something I've not seen yet, so that's new. Still, my pointer is on the A. In this case, I'm doing a breadth first search here. So the next I would discover would be C, because it can be reached from A with another edge. So I put C over here. Now I have exhausted everything I can reach from A in a single step. Now I move on with my pointer here to B and see what I can explore from B. Now here I would find the E and nothing more, because this here is directed here, so I can't go this way in this context. I could obviously ignore the direction, but this is not what I'm doing here. So the next would then be that I go back to C, which is the third here, put my marker up here, and then find the D, find the J, then try to explore from E, where there is nothing to be found, try to explore from D, and so on until I have reached all of the graph. Or I have reached the limit of the depth. Anyway, the details again don't matter. What matters is that this algorithm runs around in the graph and tries to explore it and find something from a certain place. And there's a lot of variance to this. You can do depth first search, in which case you would first go further and then backtrack and so on. There's the possibility for shortest paths. You would typically take the source and the destination of your path and work in both directions until it meets, and things like that. Sometimes you would consider weights and so on and do the ordering here slightly different. There's a lot of possibilities, but the fundamental idea of what a graph database is good at is searching in a graph. And as you can see, what you find this way is paths. So that is the recurring pattern. We find graphs, paths in a graph according to some pattern. And all the queries I showed you essentially can be done like this. So what matters here is that if you send a single query to that database, which asks one of these graph questions, behind the scenes on the server, before there's more interaction going on between client and server, it does something like that. And so what it needs is a very, very fast way to find from a vertex where it sits all the neighbors. And that is what graph databases are good at. So here you can already see the theme of this talk. If you have queries, as I mentioned in the beginning, then a rather obvious idea is to store the graph in a graph database and do the queries there. So that will be the story of this talk. But I want to go one step further. Because as it turns out, graph databases are nice, and if you have a purely graph problem, then they are the right tool, then they are the right hammer for the nail you have. But it turns out that quite often another tool in your box is even more versatile, namely a so-called multi-modal database. By which I mean a data store that is at the same time a document store, JSON document store, a graph database, and a key value store. And I have not much time today, but the crucial combination of these three data models is that they fit well together. So it's a good thing to store your vertices and edges in a document store, because quite often the labels and types and so on of your edges and vertices are diverse and not very uniformly structured. And since a document store is essentially a key value store where the values are JSON documents, and JSON is very versatile, it is easy to combine a key value store as well. And again, as with every database question, the crucial thing in this combination is not that you put multiple engines in one data store, which you don't actually, but that you have a common query language where you can mix your graph queries with your other queries. In the same query, ask even more complex questions. So the crucial thing here is that the particular combination of data models we have put in here is such that we don't have to make compromises for each data model. Such a multi-model store can actually compete with specialized products on their own turf. So such a thing can be a document store and compete with a specialized document store, and there's no compromise being made. It can compete with graph databases as long as the graph queries are implemented and there's a very fast indexing for the neighbors. Therefore, if you have such a tool, you can do the polyglot persistence, which means you take the right data store, the right data model for the data you have, one step further, because you can do it with a single database technology. Okay, I'm deviating a bit. Just to say, a multi-modal approach is a store which is not only a graph database, but is more. Typically, these days you talk about microservice architectures, and you should not think now that in such a big microservice architecture, you reintroduce the monolith by putting one of these data stores in the middle. That's not the idea. The idea is that if you have a large project and you need a graph database and you need a document store, then you probably deploy a graph database in this part with this technology. You deploy a document store in the other corner of your project, separate instances, but the same technology. And in these cases where you actually need these multi-model queries, you can use them in one part of your project. Okay, I have to admit that I bring this idea up not without some kind of background interest. I work for a company who builds one of these things, and that is what I want to demonstrate later on, just to suggest a new tool in the box. So ArangoDB is a multi-model database, and the two crucial aspects I want to emphasize today is that it has a query language which can do transactional semantics, joins, graph queries, all in one language. Yeah, and so obviously today I want to focus on the graph capabilities, but for the full context, I would like to emphasize that you can do things like run a graph query, and for every thing you find, regardless of the depth, you do a join operation to some other collection, say. And these are query facilities you do not have in a pure graph database, and you don't have in a pure document store, but in a multi-model database you can do this. So AQL is similar to SQL. It is not SQL, because SQL is good for tables and not so good for graphs and for documents. So therefore we have deviated from that, but in spirit it's the same. You describe what you want, and then there's a query optimizer which behind the scenes looks at the query, parses it, optimizes it, and distributes it across the cluster. One more thing I should mention about ArangoDB before we look at more details and see it in action is that it is a data center operating system application. So the idea here is that you don't want to go through a tedious process of installing ArangoDB on 10 machines and then maintaining it and so on and so on. No, you want to run a cluster with some operating system, and then you want to click and install a distributed database exactly as you install an app on your phone. That's what you want, and that's what you get. You get automatic resource management, you get better resource utilization, and you get fault tolerance, self-healing, and automatic failover, and so on. Currently, ArangoDB focuses on Apache Mesos and DCOS, but it's relatively straightforward to set it up on other resource management things. Anyway, back to the topic. The point I want to make here is that if you are in a situation that you have some kind of infrastructure already running, you maybe have a yarn with Hadoop in it and so on, and Spark already in your infrastructure running, then these infrastructures lend themselves very easily to plug in another tool. Because problems like software deployment, resource management, service discovery are solved for you already. Yeah, so therefore, you can just, if you have another tool in your box, you can these days just say click, click, and then there it is, and you can use it. So the example I want to talk about today is that if you have HDFS, Hadoop, Spark, and ArangoDB installed in the same infrastructure, then the idea to take your graph data you might already have sitting in HDFS and just additionally copy it into ArangoDB for your ad hoc queries is not only a nice idea, it actually is very practical because you just do it. So let me explain what's going on. And again, the details don't matter, but imagine that you have maybe two files with vertices and edges, and this is an example where I have, I think, all patterns since 1975 till 1999 in the data store. I got this from the Stanford graph database, graph example data set. And then there's citations. So the information, the edges are which patent cites another patent. Yeah? Then what you essentially have to do is you drag your files out of Hadoop. And obviously, one could simplify this by making the importer aware of Hadoop as well. Then you essentially do click, click, or a single command line to install an ArangoDB cluster, which you can then scale up and down as you need for capacity. Then you need essentially 3 commands to create a graph in there that is similar to what you earlier saw in Spark with a graph frame. Well, this way, here we first create the graph with empty collections, and then we run 2 imports, and after a few minutes, you have several gigabyte of data as a graph in your graph database, and you're ready to go. So, what can you then do with it? I'm showing just 4 examples here because of the lack of time, just to make a point. So if I, for example, start with a certain patent and ask for a graph traversal of depth at most 3, that is, I ask for all the patents which are cited in this patent application, and then everything which was cited from them, and then everything which was cited again one more step. So up to 3, the depth is not known to me. Then I would write something like this. This is in the AQL query language. I just say start here, no, return the V's, start here, use this graph I just made, go outbound, and here you go, you get 500 results back in 317 milliseconds. That's not bad for a quick query. Oh. Here's an interesting one. Sometimes I look at a patent, I want to somehow see similar ones. So a good idea is to just follow the citations one step forward. That is, take all the patents which are cited by this one, and then from whatever I get, I go one step back to see what other patents cite the same things. That is probably a similar patent. So to do that, I go one step forward, and then from there, where I am, one step backward, and I exclude the one where I started. And again, that's a very ad hoc query which you might have in a web user interface or something like that. And this gives you all the 35 results in 59 milliseconds. So that is the kind of latency I'm talking. Smallish queries, but you want to have them very quickly. If you have this facility, you can have a web front end, which for every user who clicks on a patent, immediately shows similar ones. Yeah. Let's look at 2 more examples. Here we go backward. So we ask, this is a patent, which patents have cited that one? And then in turn, which ones have cited those again? So that goes from something else 2 steps back. And again, few results and very quick execution. Now, you can do other things. You can just look for the number. For example, if I start somewhere in the past and I want to have a count about what other patterns have cited this one recursively, then I just say, well, upper bound 10 maybe, I could have set 20 here. And after 311 milliseconds, I just get back the number 398. Right. And just to show you that this is real and not some story, I will just run these queries live. I have to admit, this is not in a cluster. This is at this stage running on my laptop, but it simulates a cluster, so it is very similar. So if I, for example, have this one, this is up to 3 steps. I can execute this, and you see after 288 milliseconds in this case, I get a list of all the patterns, and these are JSON documents. The key is the primary key here, and I get the year of the application, and so on and so on. And just to make a point, I can change this here in the query editor and ask for the full path as well. Oops. Oh, yeah, okay. I want to make an object out of that. How can I scroll down? Okay, now the display takes a bit longer because there are paths. So you can see it not only gives you the pattern itself, but the whole path here. That is vertex edge, vertex edge, vertex edge. That's another thing a graph database can do. The results need not be single data documents, but you get the whole paths. So maybe let's do one more. For example, this similar patterns thing. This was this query here, and if I just execute that, you get 35 results. Or maybe one more. This is the count backwards, collect with count into, execute, and the answer is 398 after 294 milliseconds. So I guess that is the major point I want to make. If you have somehow queries which should be really fast, but for some user interface or some interactive tool or whatever, you want to have multiple such things quickly, then the message is very simple. Don't just keep the data in HDFS and run a Spark job for everything. Rather, import your data into a graph database, run the query here, and that's it. Now, I want to finish with just one more remark. This is the story I wanted to tell in this talk, but there are other stories I could have told. For example, sometimes the graph data you have changes in a transactional way very rapidly. And then Hadoop is not the right answer, because things are changing rapidly. You can only append to files and so on. So then you want to probably turn things around. What you want to do then is that you do the transactional changes directly in your graph database, because it's a database, therefore it can do these things very nicely for you. And do your low latency, quick real-time queries, exactly as I said, on that database. So you have quick answers, and you have it on the most recent set of data. And then, of course, you can regularly dump your stuff out to HDFS and still go on with Spark and run your analytics on slightly older data. Again, a good use case, but this is a different story, and I'd like to tell it a different time. Let me just say that you can even use our Spark connector and directly run Spark jobs on data that is sitting in ArangoDB. But here's a link, and I've prepared a few other links here. And in particular, whatever I do in this example will be written up in the next few days in one of the demos in the last link here. And I'm happy to answer your questions now if you have, because I'm finished.
Yeah, I was wondering, is this approach also suitable
Yes, let me just repeat the question. Is it also usable if the edge has a length or weight or geolocation or whatever? Yes. So in ArangoDB, vertices are JSON documents and edges are JSON documents, and you can put arbitrary data there. And since it's a multi-modal database, you can do arbitrary additional queries. So you can use a geo-index to find edges. You can, in the shortest path, you can say this attribute shall be the length of the thing, and then you can do shortest path with respect to that length. And you can do filtering according to the attributes you have on the edges. That is all possible. And that is, again, a case where the combination of document store and graph database is very suitable. Yes, there is. It's always a bit of a problem when the graph gets out of hand. So therefore, I've not even bothered to show it. But what we have is some kind of visualization here. This now starts at a random vertex, shows the outgoing arrows, and you can explore and click and move around. I should say that when the graph has 1 million vertices and edges, then quite often this is not sufficient. But obviously you can export data to other visualization tools as well. Yes?
What's the consistency versus availability choice in ArangoDB?
Okay, ArangoDB is distributed. You can configure replication, so therefore you have high availability. But the choice is CP, that is, it is consistent and not available in form if the network is split. Can you say this again? Yes, so we have a lot of libraries, and JavaScript is among the ones which we maintain ourselves. So that's for Node or for the browser directly. And what I have not mentioned is that a lot of the higher level API is actually already implemented in JavaScript. So V8 is embedded, and you can even extend the HTTP API by your own routes. So if you have something data-centric which you need, you can even deploy your JavaScript code to the database and run it on the coordinator, such that it has very fast access to the data and expose your own services. But we have lots of other languages, Java, C++, and so on. Further questions? Yes?
Yeah, you said the data is distributed, but are the queries themselves distributed?
Yes. Yeah. Having said that, of course, data distribution, automatic data distribution in a graph database is a very bad story. Because the moment you naively distribute your data all across your cluster, the moment your graph queries, your traversals will be slow when they have to do lots of network hops. So therefore, stick with one server as long as you can for a graph database. But if you need to, then do some intelligent sharding. And so what we offer is something we call the smart graph extension. You can specify an attribute of your vertices, which is used to do the data distribution. Now this leads to if you do this right, and obviously you have the best domain-specific knowledge about your data, if you do this right, you can make it so that most edges are local on a machine. And the database can take advantage of that. And what happens then is that the query optimizer looks at the graph traversal and it says, okay, we are here, this server is responsible, and so as much of the traversal as is possible is then done on that server. So the computation is moved to the server, and the open questions about edges which go to another server are then moved back, and then further questions are sent in parallel, such that this query can be executed very efficiently. But it works best if the user has domain-specific knowledge about the graph and can help the database. Okay, I don't see any questions anymore. Feel free to contact me afterwards. Obviously, the conference is over, but I have cards here. You can have my contact. And I even have some T-shirts with ArangoDB if you want. So thanks, and have a good trip back.